At 1:23 in the morning on April 26, 1986, Chernobyl Unit 4 was running a low-power electrical test. Inside the reactor, conditions were becoming unstable. In the control room, there was no single trustworthy number that showed the danger as a complete picture. The familiar version of this story says one radiation meter stopped at a low maximum and convinced everyone that the accident was manageable. That exact anecdote is repeated often, but it is not established in the authoritative reports used here. The documented failure was larger than one instrument. Before the explosion, important parts of the core were difficult to see. During the final seconds, the event moved faster than the main recorders could follow. After the explosion, the radiation map outside the plant had to be assembled from incomplete measurements and later reconstruction. This matters because the Chernobyl accident was not only a failure of reactor physics. It was also a failure to turn dangerous conditions into information that people could understand and act on in time. To see why, begin before the emergency button was pressed, while the reactor was still operating and the control room was trying to hold it at low power. The RBMK reactor was enormous, roughly 7 meters high and almost 12 meters across. Different parts of that core could behave differently, especially at low power when the distribution of neutron flux could become uneven. In the operating configuration described by INSAG 7, there was no in-core instrumentation available at low power. Operators mainly relied on detectors outside the core. Those detectors could estimate total power, but they could not show the internal shape of the neutron field. The report says that, under those conditions, an operator had to rely mainly on experience and intuition rather than on control system readings. That is an extraordinary burden in a reactor whose local conditions could change without appearing as one clear control room signal. One crucial value was the operating reactivity-margin, or ORM. It described how much control rod capacity remained in the reactor. The computer needed roughly 10 to 15 minutes to cycle through thousands of inputs and calculate it. That was useful for steady operation. It was not a live warning system. The value was not conveniently available to the operator, and it was not built into the reactor protection system as an automatic trip. The RBMK used water as coolant and graphite as moderator. Under the conditions of the accident, more steam bubbles in the coolant could add reactivity instead of reducing it. More power created more boiling. More boiling could create still more power. This positive void coefficient made the reactor unusually sensitive to disturbances in coolant flow. INSAG 7 concluded that both the void coefficient and the overall power coefficient were positive at the time of the accident. The emergency control rods contained graphite displacers. When fully withdrawn rods began moving down, their first movement displaced water in the lower part of the channels. In the accident configuration, that could briefly insert positive reactivity before the absorbing section arrived. The effect was known as positive scram. The first instant of a shutdown could make part of the core more reactive. The full rods also took about 18 seconds to insert, far too slow to control the rapid excursion that followed. At 1:23:40, the senior reactor control engineer pressed the emergency stop button. INSAG 7 says the reason for pressing it could not be established with certainty. 3 seconds later, the protection system recorded a runaway rate and power above 530 megawatts thermal. The next seconds destroyed the reactor, but the exact sequence was not captured like a modern high-speed data log. The official investigation said the event developed faster than the resolving power of the reactor parameter recording devices. The standard recorders were designed for relatively slow processes. They could preserve extreme values, but they were not suitable for reconstructing fast transients. The centralized Scala system calculated major reactor parameters about once every 5 minutes. Another diagnostic program recorded hundreds of signals, some once per second, but it did not record several main reactor parameters directly. Of 211 control and protection rods, it recorded the positions of only 9. Investigators therefore had to combine instrument readings, time corrections, physical models, electrical oscillograms, operating logs, and witness accounts. Even some witness accounts disagreed about the number and sequence of explosions. The broad conclusion is strong. The positive void feedback and the control rod design created a destructive mechanism. But the report also states that the exact initiating sequence may never be known with certainty. After the reactor was opened to the atmosphere, the measurement problem changed. The question was no longer only what happened inside the core, but where radioactive material traveled, what people encountered, and what doses they received. UNSCEAR reports that iodine-131 and cesium-137 were especially important for public exposure. Iodine-131 decays quickly, with a half-life of about 8 days, so the opportunity to measure its deposition pattern was brief. Because of the emergency and that short half-life, few reliable measurements of iodine-131 deposition were made. Scientists later reconstructed parts of the pattern using other radionuclides, environmental samples, human measurements, food records, and models. That does not mean every first estimate was deliberately minimized. UNSCEAR says early population dose assessments often used cautious assumptions and generally overestimated doses. Larger measurement sets later improved the estimates. The deeper lesson is that a number without its instrument range, location, time, isotope, and uncertainty can be dangerously incomplete. At Chernobyl, different numbers answered different questions, and some answers arrived years later. The authorities evacuated Pripyat and then surrounding settlements. UNSCEAR records that 115,000 people were evacuated in 1986, with another 220,000 resettled later. For the public, one of the most important early pathways was not a dramatic external dose. It was fresh milk contaminated with iodine-131. Timely controls on milk and animal fodder could have reduced thyroid exposure, especially among children. UNSCEAR concluded that implementation of those countermeasures in the Soviet Union was flawed because timely advice was lacking, particularly for private farmers. The information failure had moved from the control room into everyday decisions about food. At the plant, 2 workers died in the immediate aftermath. Among plant staff and emergency personnel, 134 developed acute radiation syndrome, and 28 of those people died from it. Those figures describe a defined group with high acute exposure. They should not be turned into unsupported claims about every later illness. UNSCEAR separates observed effects, dose estimates, statistical projections, and outcomes that cannot be attributed with certainty. The first international account placed heavy emphasis on operator violations. INSAG-7 did not erase operator responsibility, but it changed the balance by incorporating new evidence about the reactor's design and the positive scram effect. The later report identified defective control rods, dangerous positive feedback, inadequate procedures, weak safety culture, and failures to share earlier warnings from other RBMK plants. It also said the type and amount of instrumentation, and the control room layout made unsafe conditions difficult to detect. After the accident, RBMK reactors received additional absorbers, higher enrichment fuel, faster shutdown systems, updated operating instructions, and changes intended to reduce the positive void coefficient and the positive scram risk. Chernobyl did not happen because one person failed to read one dial. It happened inside a system where the reactor could enter a dangerous state. The instruments could not present that state clearly, known design hazards were not effectively communicated, and the final event outran the recorders. The most important safety instrument is not a meter by itself. It is a system that makes danger visible early enough for people to respond before the numbers become a reconstruction.